this is now we're getting into new stuff. For molecular solutes, the concentration usually represents the concentration as it actually exists in solution. So if you dissolve sugar and you have 1 molar sugar, that's 1 mole of sucrose atoms, which I think is C12H22O11. All right, so the concentration of sucrose in a solution would be however many of those sucrose molecules exists. When we dissolve these ionic compounds, we're getting 1 calcium. So in a 1 liter of 1 molar solution, we would have 1 mole of calcium ions, but we would get 2 moles of those chloride ions. Because for every one of those that breaks apart, we get 2 chloride ions off of it. So the concentration of the individual ions can be approximated from the overall concentration. We got one example here. I'm not going to spend too much time on this, but if you want to determine the molar concentrations of calcium and chloride in a 0.75 molar calcium chloride solution, so 0.75, I should write this as molar calcium chloride. What would the concentration of calcium be for this solution? You don't even really have to do math to figure it out. Yeah, it would still be 0.75 molar Ca2+. Right? So this is saying that we have 0.75 moles of calcium chloride units, but in the solution those break apart. So we're only getting 1 calcium. So then it's this concentration times the 1 calcium gives us 0.75 molar. So what would the concentration of the chloride ions be? Yeah. So if we take the 0.75 and multiply multiply by the number of calciums, that gives us 0.75. Then for the chloride ion concentration, we just take 0.75 molar and then multiply it by the fact that we have 2 chloride ions. So we take 0.75, let me write it down here, 0.75 molar times 2 would be 1.50 molar calcium ions. So for any concentration of an ionic compound, you can figure out the approximate concentration of its constituent ions. So let me just do one more example here. Let's say we have let's make it easy, 50 molar aluminum chloride. What would the concentration of chloride ions be for that solution? Somebody new? For chloride ions. So here we took this and we multiplied by the fact that we have 2 chloride ions. So we took this multiplied by 2. So yeah, multiplied by 3 because we have 3 chlorines for every unit. So we get 1.50 molar. So I guess the same as this one. And then the aluminum concentration would be the same, 0.5 molar, right, multiplied by 1. Okay, like I said, not spending much time on that. One of the more common things that you have to do if you work in a chemistry lab, or even in a biology lab, is to do dilutions, right? So the solutions that we have in the stock room, which are stock solutions, are concentrated forms because they take up way less space. Right? We've got more atoms of whatever we're interested in a smaller space. Oh, I forgot to put my ring back on. Many lab procedures call for less concentrated solutions, though. So we have to dilute that stock solution and make it less concentrated. So we can do this by combining a certain amount of the stock solution with water. So we're just diluting these with water. It's kind of like those Mio drink mix things where you squirt the concentrated drink mix into your water bottle or whatever, shake it up, because you don't want to drink the concentrated stuff. It tastes very bad. So the equation we use for this, and this is, well, it'll be repeated on the next slide, but only use this for dilutions. This will not work for stoichiometry problems. But we use this M1V1, which is the molarity of one compound times the volume of that solution is equal to the molarity of a second solution times the volume of that solution. And what's happening here is we're sort of removing volume from the equation, because if we took molarity equals moles over liters. So liters is a unit of volume. So if we take moles over liters and multiply that by liters, we'll get moles. And then on the opposite side, we're doing the same thing. We're taking moles over liters times the volume of that solution, and also just ending up with moles. So when we're doing a dilution, we're saying that I want, some number of moles of my solute in my new solution, but I want it in a different volume. So we're just really calculating the number of moles that we need to add to make our diluted solution. So again, this only applies to dilution. Only applies to solution dilution, does not apply to stoichiometry. And when diluting acids, you always want to add the concentrated acid to the water. You never want to do the opposite, because when you dilute acids, they generate a lot of heat. So if you put the water into the acid, there's less volume to absorb that heat, and it can quickly go from being a room temperature solution to boiling, and then you have boiling acid, and then you're splattering acid everywhere, as well as making concentrated acid vapors. And then you have to, first off, not breathe the concentrated acid vapors, but also clean up that mess. And it's not fun to clean up concentrated acids. But if you have a body of water in your flask, and you pour your acid into that, there's a lot of water to soak up that extra heat that's generated without boiling, splattering acid, or creating acid vapors. So always acid into water. All right, so here's a solution dilution problem. How much of our 6 molar sodium nitrate solution should you use to make 0.585 liters of a 1.2 molar sodium nitrate solution? All right, so we have a concentrate, and we have our new concentration that we want and the volume of that we want. So our equation is M1V1 equals M2V2. So we're going to have M1, and we're going to have a V1. We're going to have an M2 and a V2. That should be a 1. So while it doesn't really matter which way we put these into the equation, as long as we keep these two related numbers together. For example, this is 0.585 liters of this solution. So these two together are going to be either V1 and M1 or V2 and M2. To sort of match the way that this question is worded, let's make the 6 molar, that's our M1. So 6.0 molar sodium nitrate. And then our V1 is what we're solving for, right? That's because the question says how much of the sodium nitrate solution. And then we want to make a 0.585 liter solution, and we want its concentration, or M2 in molarity, to be 1.2 molar sodium nitrate. And then we can just plug these in. This is going to be 6.0 molar NaNO3 times V1 is going to be 1.2 molar sodium nitrate times 0.585 liters. So we're going to take our 1.2 times 0.585. That's going to be 0.702. And then the units here, remember molarity equals moles over liters. So our units now, because we multiplied liters by moles over liters, is just going to be moles of NaNO3 equals V1 times 6.0 molar NaNO3. So we can take our 0.702, divide it by 6, and our volume of the 6 molar concentrated solution that we're going to need is going to be 0.117 liters of the 6.0 molar NaNO3. And this actually would be 2 sig fig, so it should be 1.12 liters. Questions? Confusions? Mm-hmm.
Can you walk through how we got the 0.117 liters from the volume of the moles? Where it says 0.702 moles of the NaNO3.
Mm-hmm. And we
put that into the molarity formula?
We divided by the 6 molar on both sides.
Okay, to get the volume, right?
To get the volume.
Molarity formula.
Mm-hmm. So if we take moles and we divide it by molarity, actually, let me write it this way. So moles divided by molarity, and molarity is moles over liters. This is a math trick. So if you have something divided by something else, we can take that something else, the moles over liters here, and we can flip it, and then instead of dividing, we're multiplying. So this moles times liters over moles. So when we divide moles by molarity, the moles cancel out, and we're left with liters. Any other questions? Okay. So this is, in some ways, this is a bad example of how to make a concentrated or a diluted solution, because they're adding the stock of the acid. Well, they're adding a salt solution here, so it's not that bad. It's actually not bad at all. So this is just a salt solution. It's not an acid. They're adding it into a volumetric flask. Saw these before. They're just very, very accurate at measuring out a single volume. So this would be a 5-liter volumetric flask. You add your stock solution. You add actually there's a step in between here where you add most of the water, but not all of it, so that you can still mix it easily. Because the one thing that these things do lack is when you fill it up to the top here, they're very, very hard to mix because there's only this small amount of air. So you actually have to turn it like up and down like 50 times. You should probably do more for it to mix. But then once you've diluted your concentrated stock up to the line, then you've made your diluted solution. Okay, now for the fun stuff. In reactions involving aqueous reactants and products, right? So you've got a reaction happening in water. It's often convenient to specify the amounts of reactants or products in terms of their volume and concentration. Because it's very easy to measure volume, and concentration gives us a way to go directly from that volume to the actual number of moles. So it makes doing the stoichiometry easier. So we can use our volume and concentration to calculate the numbers of moles of reactants or products, and then use the stoichiometric coefficients to convert the other quantities in the reaction. So do you want to highlight here, this will be our third way of doing stoichiometry problems. The first one we talked about was just if you have grams of a reactant or grams of a product. The way these problems always go, if you want grams, so let's say our thing here, we have grams of A, and we're trying to calculate grams of B. So if we have grams of A in any stoichiometry problem, we have to convert that to moles. And then we could do that using the molar mass. And then once we have moles of A, we can use the stoichiometric coefficients. So those are that's what we did today, right? The numbers that you put on the balancing problems. Those are the stoichiometric coefficients. We use those and that ratio to convert it from moles of A to moles of B, and then we can use the molar mass of B to get to grams. The other way that we had to do this was from the gas law stuff, which we didn't test on and was before spring break. But hopefully you have some recollection of this. If you have the pressure, let me make that a comma, the volume and the temperature, you can use that to calculate, this is pressure, volume, and temperature of A if it's a gas. You can use that to calculate the moles of A. And then you can use the stoichiometric ratio to calculate moles of B, and then you can go to grams of B, or if it's a gas law problem, stoichiometry problem, you probably are calculating the volume of B. Yeah.
So from going from moles of A, you're going to use the, like what we just did, like the coefficients for the balancing equation. So basically the ratio, right?
Yes.
Okay.
Yep. Yeah, just the ratio. So for equation, let's do something like A plus C reacts to form B. And let's say that this is 3 and 2, just to make it interesting. So yeah, then for every 2A, the ratio between A and B would be 2 to 3. So the one we're going to talk about now, because we have you've acquired the concept of molarity now, we can go straight from a volume of a solution. So if you have the volume and the concentration, again, of A, we can use that to calculate moles of A. And then the stoichiometry problem just becomes the same as the other ones we've done before. Use the ratio, you can calculate moles of B. And in addition to be able to calculate moles of B, we can calculate volume of B, volume of B, or we can calculate the concentration of B, depending on what the question's asking for and what numbers you're given. So it's sort of this pathway that we're going to be talking about right now, but there will be questions on the final about the other ones. But when it all boils down to it, they're kind of the same type of problem, which is why they're all called stoichiometry problems. So again, right, we're going to be doing volume of A to moles of A, and then using that stoichiometric ratio to convert it to moles of B. Oh, I actually didn't do it. Okay. So one of the key things about these problems is that we need to work in units of liters and not in units of milliliters, because molarity, which is capital M, is moles per liter. So for the units to work out correctly, we need to do this conversion. So for this problem, how many milliliters of 0.112 molar sodium carbonate will completely react with 27.2 milliliters of 0.135 molar nitric acid according to the reaction? And here we're looking for milliliters. Right, so we know that milliliters of our sodium carbonate solution is what we're going to be trying to find. So ultimately at the end here, milliliters of Na2CO3. So let me try asking this question. We're going to be getting liters of this, liters of Na2CO3 first, and then we'll have to convert liters into milliliters. What piece of information would we need to calculate how many milliliters of sodium carbonate we would need?
The ratio?
The ratio is part of it, yes. We do need the ratio. But the ratio helps us to get what? Moles, right? We need to know how many moles of sodium carbonate there are. So to be able to calculate the liters of sodium carbonate, we need to know the moles of Na2CO3. And then how would we get the number of moles of sodium carbonate?
The moles of...
You're on the right track?
Sorry, yeah.
Oh, nitric acid, yeah. HNO3. Yeah. So we could, let me write this, Na2CO3. In theory, we can get it from the moles of anything else, but we have the numbers, or we have numbers associated with nitric acid. So we wouldn't use anything else because we don't have any numbers for those. And then to get the moles of nitric acid, what would we use to get the moles of nitric acid? Molar mass is one way we could get it. Yep. But we don't have the mass of our nitric acid. We have a volume of nitric acid and the molarity of nitric acid. Yeah, we'll use the molarity and their volume to calculate the number of moles. But we do need to first convert our number of moles into liters, because again, molarity is moles per liter. So I have the conversion, wrote it up here ahead of time. To convert from milliliters to liters, we just take our milliliters and divide by 1,000. So it'll be 0.0272 liters of nitric acid. So from our starting point here, we should shift this over a bit. We're going to start with 0.0272 liters of nitric acid. And then we use the molarity, which is 0.135 moles of HNO3 per 1 liter. And then we use our mole ratio between nitric acid and sodium nitrate, or sodium carbonate, sorry. So we have 2 moles of sodium nitrate, or nitric acid, 2 moles of nitric acid for every 1 mole of sodium carbonate. This will be 1 mole, Na2CO3 for every 2 moles of nitric acid. And now we can go from moles of nitric acid to liters of nitric acid using the molarity, not nitric acid, sodium carbonate. We can go from moles of sodium carbonate to liters of sodium carbonate using our molarity. And again, because this is moles per liter, we'll have to flip it. So it'll be 0.112 moles of sodium carbonate, or 1 liter of sodium carbonate. And then we just need to convert from liters to milliliters. And now we can just multiply across the top and divide by the bottom. So 0.0272 times 0.135 times, right, we can skip the times 1 times 1,000. And then divide by 2. And then divide by 0.112. So the answer here is it would take 16, 3 sig figs, 16.4 milliliters of sodium carbonate. Yeah.
I have a question for the 0.112 moles of the sodium, is it chlorine?
Carbonate.
Carbonate. The sodium carbonate. So we use the 0.112, and that means molarity, correct?
Mm-hmm.
So molarity would count for moles in that situation?
Yeah, so molarity is moles per liter.
Okay. Yes.
So whatever that number is, yeah, let me see. Yeah, so 0.112 molar equals 0.112 moles per liter. So we can take that, it's a conversion factor, so we can flip it upside down if we need to. Are there any other questions? Okay. Got at least one more of these. I should have converted these ahead of time too. In the interest of time, this is 0.0250 liters and 0.0357 liters. So just converting those milliliter values into liters. So if we know the volume of a sample and we calculate the number of moles, we can calculate the concentration because we take moles and we divide it by liters. And so that's the goal of this problem. So we have a 0.025 liter sample of nitric acid, and it requires 35.7 milliliters of 0.108 molar sodium carbonate to completely react with all of the nitric acid in solution. So what is the concentration of the nitric acid solution? First of all, what's missing from this problem? We're missing a key piece of information, which if you remember how to do it, you could probably write out, but the chemical equation's missing. So we don't know what the ratio is between nitric acid and sodium carbonate. We can, though, use the wording that we have here to figure it out. So we have nitric acid, right? So we have a nitric acid solution, requires some amount of sodium carbonate. So it's Na2CO3. To completely react, what is the concentration of the nitric acid solution? So our products here are really going to end up being just a double displacement reaction. So we swap the sodium and the hydrogen to get sodium nitrate plus H2CO3, carbonic acid. It's one of the nomenclature answers from last week. And now we can balance it. I might give you one problem where you really have to do all of this, and that would be like the very, very last problem on the exam. Most of the time, I want to test the individual things, so we'll give you a balanced equation. Otherwise, it's like, well, if you don't balance the equation, you can't write the equation, then you miss everything on it. Yeah. There's no reason to stack up points to miss like that. Okay, so we got to balance this. Let's start with the hydrogen. So we need 2 hydrogens on this side because we only have 1 on the left, and we need 2 because there's 2 on the right. And then we'll take our nitrate, because now we have 2 nitrates. So we need 2 of those on this side. So we add a 2 there. And there's 2 sodiums, and then 1 carbonate on either side. And if you were wondering how I knew that carbonic acid needs 2 hydrogens, it's because carbonate is one of the polyatomic anions, and it has a 2- charge. So you have to give it 2 hydrogens to balance that charge. And then if, for whatever reason, gas evolution problems really stuck with you, you'd realize that this would turn into H2O and CO2 gas. Yep.
So when you were balancing them out, how did you get 2 hydrogens on this one when the example was?
Oh, these 2 hydrogens? That's because carbonate has a 2- charge. And so it takes 2 hydrogens, because every hydrogen has a +1 charge. So I have to give this 2 before we even start balancing the coefficients. Yeah, so the first step in predicting products is to write out the products correctly. So to write out this correctly, you have to have 2 hydrogens. Alrighty. So now we've got that. And our question is, what is the concentration of the HNO3 solution? So we have the volume of the nitric acid. What is the piece of information that we're missing? So molarity is moles over liters. If we have liters, what are we missing? Moles. So really here, we're just trying to get to moles. So the last problem, we kind of worked it backwards. This one, let's try working it forwards. So if we want to get to eventually, right, we're going to need the moles, HNO3. That's our target. we can start with the things that we do have, which is this 35.7 milliliters of 0.108 molar sodium carbonate. So we start with, I want to do this, put this here. And I'm going to use the converted volume here. So we're going to do it in liters. So it's going to be 0. Wait, how do I redo? Oh, there we go. So this is 0.0357 liters of Na2CO3. So we're starting with liters, Na2CO3. And if we want to get to eventually moles of nitric acid, what's our first step? What are we trying to do in every stoichiometry problem? Yeah, convert to moles. So we're going to go from liters of this to moles, and we can use the concentration that we were given of that sodium carbonate. So that'll get us to moles, Na2CO3. And then really this arrow can go all the way over, because with the balanced chemical equation, we can use our ratio to get moles of nitric acid. So like I said, we're going to use the concentration. So 0.108 moles Na2CO3, and that's per 1 liter. And then what is our ratio between nitric acid and sodium carbonate? 2 to 1, right? 1 sodium carbonate, 2 nitric acid. So nitric acid is what we want, so that'll go on top. That's units of moles. And then 1 mole Na2CO3. And that will calculate for us moles of nitric acid. So 0.0357. So take this, multiply by 0.108, and then multiply by 2. So it's going to be, should put equals here, 0.0077112 moles. And then we take our number of moles and divide it by the volume that we were given in liters, so 0.0250. So that our concentration is 0.308 molar, capital M, HNO3. Yeah.
So the concentration is the same thing as molarity, right?
Yes.
Okay.
Yeah, so it's kind of like saying, and this is actually on the practice exam, there's going to be a section that is like, match, or what type of units are these, right? So grams are units of mass. Moles are a number of atoms or molecules. Liters is volume. Molarity is concentration. Yep. Any other questions? Cool. All right. So that's the last molarity stoichiometry problem. And then we can get through these pretty quick. So we're going to do freezing point depression and boiling point elevation. And then we're briefly look at osmosis. I'm mostly going to glaze past those. Not going to get tested on it. So colligative properties, I think, are actually kind of an interesting category of properties. So colligative properties only depend on the number of dissolved solute particles, not the type of those solute particles. So it doesn't matter what you dissolve into your solution, it will affect a colligative property. So for example, adding a non-volatile solute, something like salt, to a liquid extends the temperature range over which the liquid remains a liquid. So this is called freezing point depression because it makes the freezing point lower, and boiling point elevation because it increases the boiling point. So actually, if you make pasta, if you actually follow the directions that are on the box, which I did not last night really, it says to add some amount of salt to your water when you boil it. That actually increases the temperature that your water boils at, and it cooks the pasta faster. You didn't realize this even until like maybe embarrassingly recently, but that's why I always had to add another minute or two to cook my pasta to like where I wanted it. It's because I wasn't adding the salt. So it was boiling at a lower temperature and it took longer to boil. So you can add salt, but it also lowers the melting point. This happens in like places where it actually freezes. We don't do it around here, but that's also why cars in California tend to last longer, because that salt plus water helps corrode metals, really anything. But just like we could add salt to the ice to lower the melting point, we do that because salt is super cheap. You could do that with sugar, so they could just go out and like coat the roads in sugar, and it would also lower the melting point and maybe make it less slippery, because it would be all sticky and gross. But that's why it's a colligative property. It doesn't matter what we spread on the road. As long as it dissolves into the water from the ice, it won't freeze, or it'll freeze at a lower temperature. Ethylene glycol or propylene glycol added to water, and that actually raises the boiling point. So in a car's radiator, super important because it lets your radiator get hotter without turning that coolant into steam. Because if it turns into steam, it creates pressure, and it can blow your radiator open in the drive-thru at Starbucks. Not that that's ever happened to me. Driving an old car. But it'll also lower the freezing point, so that's why it's called antifreeze, because in areas, again, where it gets super cold, you don't want the water to freeze in your radiator either, because water expands when it freezes, and it will break your radiator. Okay, now on to my least favorite unit. Freezing point depression and boiling point elevation. We use a different unit for these because, again, it just matters how much solute is in the solvent. So we use molality. I hate this word. Molality is the number of moles of the solute per kilogram of the solvent. Kilograms of the solvent. So this is important. This is important. When we talk about molarity, so molarity is also moles of solute, but that's per liters of solvent. So the solvent, see, it's confusing. Liters of solution. And the solution is the solute plus the solvent. But for molality, it's only the solvent that goes in the denominator, and in kilograms. So just remember there's a distinction there between solvent and solution for molality. Okay, so if we want to calculate the molality of a solution, kind of like when we talk about molarity, this is another unit of concentration. So we just need to take the moles of our solute and divide it by the kilograms of the solvent. So in this case, we have a sucrose solution. So our moles of solute will be moles of sucrose divided by kilograms of water. Okay? So we can take 50.4 grams of sucrose and use the molar mass, which I calculated up top there already. So grams per mole. So we'll get 50.4 divided by 342.34. So that's 0.147222 moles divided by the mass of our solvent, which is 0.332 kilograms H2O. So divide those things. This is a 0.443 molal sucrose solution. And this is why I think molality is the reason that we have to write moles as MOL instead of just lowercase m, because molality is lowercase m. Probably predates it. It's so much less useful than moles. Okay. But the one place that it is useful, and the reason that we're covering it now in relation to freezing point depression and boiling point elevation, is because that's where we use it. So there's a lot here. It's a very simple equation because the freezing point depression is just the molality of the solution multiplied by the freezing point constant for that solution. I think the one thing that does trip people up with this equation is that this is delta TF, which means that it's the change in the temperature. So when you do this calculation, it's not going to tell you what the new freezing point is. It's telling you how much lower that freezing point is going to be than the normal freezing point. I'll leave this up because it is a lot to write. So each solvent's going to have its own freezing point depression constant. These slides are also available on Canvas. Still people writing? I'd keep talking, but I'll have more to say. All right, we're good on that? Good enough? Okay. So, if you want to calculate the freezing point depression, or the new freezing point, you take, again, here's the equation, delta TF equals m, lowercase m is molality. M equals molality. And we're going to multiply that by the freezing point constant for whatever our solution is. It's the only other thing that might be of mild interest is that the units for the freezing point constant are just the opposite of molality, plus there's a degree C in there. So if we take our molality, that's 2.6, and I'm going to write this out, moles of solute per kilogram solvent. We're going to multiply that by 1.86, The units of that are degrees C, kilogram solvent, divided by mole solute. So when we multiply this, our moles of solute cancels with moles of solute, kilograms of solvent cancels with kilograms of solvent. And all we're left with is degrees C. So 2.6 times 1.86 gives us, with correct sig figs, 4.8 degrees C equals delta TF. But we're not done. The freezing point is not now 4.8 degrees C, because remember, this is for water. So for water, the normal freezing point is 0 degrees C. So 4.8 is actually higher than 0. So it can't be 4.8 because this is freezing point depression. It's depressing or lowering that freezing point. So we just say, oh, 0 degrees C minus delta TF. Or here, minus 4.8 degrees C, so that our new freezing point is negative 4.8 degrees C. So that's the last step. That's not really part of the equation. That can be easy to miss. That you have to take that freezing, you have to subtract that change in the freezing point. Okay. Boiling point elevation is, again, where you're taking a non-volatile solute, like salt in pasta water, and you're increasing the boiling point by adding that solute. So antifreeze also increases the boiling point of your engine coolant. Look at that. The equation's the same. It's delta TB equals the molality of your solution times the boiling point elevation constant. You could just write in your notes, C, freezing point depression, replace F with B. And so this one also suffers from the same well, I shouldn't say it suffers from the same problem. This one is similar to freezing point depression, where the number that you're calculating is not the new boiling point, but the difference in the boiling point. So for freezing point depression, we take our freezing point, normal freezing point, and subtract the change in temperature, or the delta TF. For boiling, we're going to take our delta TB and we're going to add it to our normal boiling point. Okay, so again, basically an identical equation, but now it's molality times K sub B. So our molality here is 3.5. Molal times 0.512 degrees C kilogram solvent per mole solute. So 3.5 times 0.512 is going to give us 1.792 degrees C. And because this is for water, we just take our normal boiling point, which is 100 degrees C, plus 1.792 degrees C, because this equals delta T sub B. So 101.792 degrees C would be our new boiling point, but with sig figs. The sig figs are a little weird here, because this is 2 sig figs, this is 3 sig figs. When we multiply that together, we only retain 2 sig figs. So this would be 101.8 degrees C would be our new boiling point with correct sig figs. Cool. Any questions about molality? So just remember that when you do these problems, you need to add it or subtract it from the normal freezing or boiling point to get your actual final temperature.
So freezing is 0, correct? And then normal is 100.
For water. So for water, normal would be, so that's where I would give you, if it was something other than water, I would tell you what the normal freezing or boiling point is. I don't expect you to memorize the freezing and boiling points of every liquid. I think that's a reasonable assumption. All right, the last thing, and we're going to talk about this very briefly, osmosis is the flow of solvent from less concentrated solution to more concentrated solutions. This really controls the flow of fluids in our bodies. So osmosis occurs when solutions containing high concentration draw solvent from solutions containing lower concentration. So really, if you wanted to personify the water wants to even out the concentration of everything. So if there's a more concentrated solution and the water can get there, it will flow across barriers to get to that higher concentration to even those out. This is why seawater is a thirsty solution. This is probably the biggest reason you can't drink seawater, because it's a very, very concentrated salt solution. That's why it tastes so awful. But when you drink it, and that comes into contact with your stomach lining and the lining of your intestines, that concentration of salt in the seawater is higher than the concentration of salts in your body. And so the water says, oh, I want to even out this concentration. I want to dilute that. So the water leaves your body to try and dilute the seawater that you drink. And so you end up getting more dehydrated rather than being hydrated at all. This one I think is actually pretty cool, where if you have a semi-permeable membrane, the water will flow from the less concentrated solution to the more concentrated solution, even to the point where it raises the level of that solution. So you could potentially lift water higher using this, or you could pump water using a difference in concentration. So this is called osmotic pressure. So on this side, we have lots of water molecules, but no salt molecules, or solute. So they flow across this membrane that doesn't let the salt through, just the water. And it actually raises the level of the water on the one side and decreases it on the other side. Osmotic pressure, like our freezing point depression, boiling point elevation, is another colligative property. So it depends only on the concentration of those solute particles. Doesn't matter what they are. Especially in living membranes, or membranes of living cells, they act like semi-permeable membranes. So, and if you eat way, way, way too much salt, and it gets into your bloodstream, it will affect the shape of your blood cells. I mean, these are super, super drastic changes, because your body's good at regulating them. So if you have something wrong, like your kidneys aren't filtering properly, and you get too much salt in your body, you could end up with a hypertonic solution, where the surrounding fluid is more concentrated in salt than your blood cells. Those blood cells have the water sucked out of them, and they end up looking like this. If for whatever reason, well, this is why you drink electrolytes, like Pedialyte, as an electrolyte solution. So if you've been doing a lot of running and sweating, right, your body loses salt as you sweat, you could end up with a hypotonic solution in your blood, where there's less salt in the surrounding blood plasma than there is in the blood cells, and so water rushes in and causes them to swell up. And they're supposed to look like these. All right, that's chapter 13.